So, should we get started? Thank you for coming. I guess there are no IX fans here. Any IX fans? Clearly not. So, what we'd like to talk about is a series of time series sorts of analyses, 3 sorts of time series analysis. Is everyone familiar with ARIMA? Have you seen the letters? Everyone seen ARIMA? Good. So we're getting to sort of started. So our approach at this point is to do sort of an overview, sort of give you a bird's eye view of each of the three sort of approaches that we can use to modeling time series. I plan on talking about a half hour, which means that I have about 10 minutes to explain ARIMA, 10 minutes to explain profit, and 10 minutes to explain RNNs. So it's going to be quite quick, but I hope, that's what I'm saying, I hope to give you sort of the overview. And if I go too quick, that's also not the point. If I'm saying things that you don't understand, please raise your hand, ask me to go back, and I'll try to do a better job. So this is more about hands-on, was our thought behind it, rather than doing sort of a lecture. That's why we're limiting ourselves to a half hour or so. So what we're going to do is, within the talk, we'll make references to the packages that we use. So for each of the sort of approaches, we'll talk to you about the packages. We've also included data. You can actually get everything now, if you'd like, from the GitHub. It's open. Just click on, well, just go to the site, go on to presentations, and you can see it's actually this final one here, is the one that we're talking about. And we also have the same version in a Python file. And so if you'd like to do that, you can kind of go through with us.
Do you have a Wi-Fi password?
Yeah, right there's the Wi-Fi. Maybe that's a nice way to do it, so then you can go through at your own speed as well, and listen to things of interest and ignore the things that aren't so interesting. So some of this will also include some of the basic code. And at the end, we have Jupyter notebooks if you're interested in having those. And the advantage of that, of course, is that everything's installed already. So it's really up to you. We can talk about that afterwards. So, and a lot of the things that we're going to try to do is talk about some of the pitfalls of each of the approaches, because learning at the beginning, learning each of the approaches, there are always things that sort of crop up that you weren't prepared for or you weren't aware that were needed to be considered. So without further ado, actually what we're trying to do is quite straightforward. And that's what actually makes ARIMA time series so interesting, because the data is right in front of you. You see the picture, you see the graph, and it's a matter of squeezing out that data. And most of the approaches that we talk about, for instance, ARIMA and profit, they're essentially looking at what happens through time. That's why it's time series. So they split up these elements of the time series in terms of this mu t, which is a long-term trend, this delta t, which is what they call a seasonal trend. And seasonality doesn't necessarily, of course, mean the weather or anything like that. It could be whatever reoccurring sort of process is occurring in your data that you want to measure. And of course, the epsilon, the famous epsilon that for the residuals, so things that are left over. So most approaches take some way of looking at these, some way of breaking these elements into their constituent parts. When we're talking about ARIMA, we're talking about really an econometric approach. So they're using a linear sort of approach. In fact, what they do to get rid of the trend is they difference the data. They're interested in differencing the data in order to remove the trend, but also the seasonal trend and things like that. Think about classic examples where you use ARIMA and profit and things like that, or say GDP growth, weather series, things like that. So there are two general sorts of approaches that we'll talk about. One's this multiplicative approach, that's the ARIMA model, and more additive approaches like profit. And this becomes clear once we look at the components again in some graphs. So we had to decide as well, do we want to use experimental data or do we want to use real data? And we quickly decided that probably experimental data is more interesting, because then we can concentrate on the actual techniques rather than the idiosyncrasies of the data. It makes things easier in some respects as well, in the sense that we have control over it. But the advantage of it, particularly when you're learning, is that you have an expectation of what it should be telling you. And that's the one advantage. So you're not fighting with trying to understand the data so much, you're fighting with the techniques. So we essentially generated data, really simple, quite straightforward data. I know I wanted a trend, and I know I wanted some sort of seasonality within it. So that was quite straightforward to do. And it looks, essentially the data looks like this. And it's quite easy to add, for instance, more randomness to it, or maybe increase the trend, or actually add an exogenous variable as well, which we want to do. So, as I said, ARIMA is from origin an econometric approach. It's in order to use it, when you're reading texts or when you're looking at, on the internet and you're looking at how to run ARIMAs, it really seems to sort of detract from the statistical underpinnings of this system. But those are really critical. Occasionally you'll see a mention of the word, you'll see that it has to be stationary or weak stationary or something like that. These are really actually the basis of the underlying model. So these are really critical that we have some understanding of this, and I'll quickly go through that. So the famous names in this are Box and Jenkins from 1970. So it's been quite around quite some time. So what is this ARIMA model? So now we can finally talk about, give an example of really what we're talking about. So we're looking at a series over time. And we're looking at, for instance, this series is what they call an AR2 series. So it's looking at how the series today is affected by the series, the previous observation and the observation before that. So it's an AR2 system. And we'll go into that a little bit more about what that means. But it's essentially what makes ARIMA so unique. And generally, whether at the end of an econometric textbook, I mean, most of the econometrics courses I took, time series was always something at the end that they sort of stuck on, because it's so much different than most econometric approaches. So, and you can imagine in the 70s, actually, it was a radical idea. So most econometric approaches, you're looking for some sort of explanatory variables. You're looking for variables to explain, for instance, if you're looking at GDP, you want to explain GDP, you look at investments and maybe labor supply and things like that. And they said, no, don't waste your time on it. If you really want to do that, it's going to be a huge model. You're going to have a hard time maintaining it, things like that. It's much smarter if you just look at the series itself and let that series, assuming those features of that series repeat themselves, then letting that data find that for you. So it's a much different psychological approach than most econometric approaches. And a lot of the econometric approaches, or all econometric approaches, have assumptions. So you've all heard about homoskedasticity, or essentially which variance through time and things like that. Time series has a special feature as well, is that a series today is very, very much correlated with what happened the day before. So you have to deal with that correlation somehow, and that's really was the innovation in the systems. So what is weak stationarity? It's generally the ones that we'll talk about is weak stationarity. It says essentially that the mu x, so the average, what everyone would call the average, is equal to the expected value of that series. So that stays essentially constant through time. And you can imagine that that's an important ingredient, especially when you're trying to predict something, because if that's not constant, then you're going to have a hard time predicting anything. And the second has to do with the second rule has to do with the covariance between time s and times t. And that has to be only dependent on the differences of s and t, so the difference in time. It can't be dependent on anything else. So in other words, this relationship has to hold in order for the model to be the best model that it can be. So what's the general strategy? Well, we've all done those courses where you plot the data, you transform it if necessary, by differencing or logging or scaling. You identify the dependencies. That's where you get these autocorrelation functions, and partial autocorrelation functions. You estimate the parameters. You do diagnostics on the residuals, and finally you choose a model. So let's just do that. So here we just generated, just loading that generated data that we did. Let's see what happens. And it turns out that this frequency is important, especially when you're looking at the residuals. It's probably not connected. Let's see. Let me try once, and if it doesn't work, then I'll just go with not doing it. Yeah, not connected. Let's see. Also log out. I'm using Jupyter Hub, but it's so fragile. Just give me a second here to run through it again. And if this doesn't work, then I'll just go without it. Let me see if it doesn't work out with swaps. Okay. Let's see if that works. Oh yeah, it seems to be working. Great. Weak stationary, Riemann strategy, reading it in. And here's actually what I was talking about previously. So this frequency is really critical. I'll show you if we get the wrong one. Oops. It's not, it doesn't, I don't like to do that. So let's forget it. So what I wanted to show is that how critical it is to get the frequency right. And this comes up a lot, and it's quite easy to do even in the ARIMA X or the auto ARIMA, is to essentially choose the wrong frequency. And the frequency that we're talking about, the advantage of having generated the data ourselves, is that essentially what frequency is referring to, if it's weekly or yearly, is the number of points between these sort of series. So that's, in this case, because we generated it ourselves, that's 50 periods. If you chose the wrong frequency, which is quite easy to do, then you won't have this sort of, you won't get this trend that pops out. And this trend is telling us, so here's the original series. Here's what the model tells us the trend is. And we put that in, we know that that's correct. And here's the seasonality of it. And so clearly we have a problem. If we want stationarity, we want weak stationarity. This is not a weak stationarity because the trend is increasing. So the solution for that is almost always the same, differencing. So essentially taking that same series and differencing it. And so what this differencing does is you can see, for instance, on the trend, it goes from a straight line to more or less random. This is more or less random. And you can see as well that the seasonality has been affected as well, but not to the degree that it's disappeared. And we'll see that in the results.
So Jeff, what does this diff actually do, this operator?
What does this, you mean in terms of the graph, or how the graphs are generated? Yeah, I'm not sure exactly what the underlying process is, how it generates it, but I think what it does is it finds the trend. That's quite easy to do. And then it subtracts off the rest. I think that that's the only thing that's going on there. Yeah. And so if you add these pieces, then you get the original series back. So it's splitting it up. It's splitting it up into the components.
And how do you find out what the frequency of your data is?
Yeah, that's a good question, and that's can get you in trouble. But it's essentially counting the number of elements between any of these sort of ridges.
Okay.
So if that's, you can have more than one seasonality within a series as well. That becomes a problem. There are ways to get around that. But generally, there's one sort of major seasonality in data. You count, you say, oh, there are 50 points between it in this case, and then you know that that's your frequency. If you get that wrong, the graphs will show that, should show that. You say, oh, I should have a straight line, or I should have something that doesn't look wavy. And so these components can help you there.
Would it make sense to just Fourier transform it?
That's exactly what Facebook does. So Profit does that. They use that underlying sort of mechanisms to do that. Yeah. And so here we're breaking in sort of our first rule. So how to read this? This is the autocorrelation function. So how a point in time is related to its previous observations. So you can clearly see that there's a pattern going on here. This is not what you want. This is a non-stationary system. So again, the autocorrelation tells you how much a series observation today is related to the previous observations. So it's a classic thing to do with a remap. You do your ACF, your autocorrelation function. You look at a picture and you sort of get a guesstimate of what you have to do to get rid of that autocorrelation. And the partial autocorrelation, this next one, is telling you actually the correlation of an observation at a particular time with another period, with all of the intervening correlation removed. So it's essentially, they do this essentially with a regression. They figure out if you're looking for the effect of say looking at an AR2 system, you say xt is equal to some constant plus xt minus 1, so xt minus 2. You run the regression and you get the coefficients on those, and those coefficients are essentially the effect of those particular variables after taking into account the effect of the other variables. So that's essentially what this partial correlation is doing. This is also telling you that, okay, it's always going to be 1 at the first one, but it's also telling you that it says there's something going on here too, that there's still correlation within the data. That means you're breaking your stationarity rules. So how do you get rid of that? You do your old friend of differencing again, and this is the autocorrelation, the first one, the ACF. And you can see by doing differencing, I've removed the majority of that correlation. Here's the original, and then the differencing. Clearly it's clearly removed a lot of the correlation. And this little blue line here is actually telling you it's a significant line. So if a dot, for instance, this dot is quite a bit beyond that blue line, so it's a suspect point. But you're also dealing with randomness in there as well, so you're probably not going to worry about these ones too much. But this ACF tells you also what your, okay, there are essentially 3 terms in a basic ARIMA. There's a autoregression term, there's a differencing term, we've talked about the differencing already, and there's a moving average term. So P, D, and Q. Not obvious why they're those letters, but those are the letters that are generally used. And so what this autocorrelation tells you is essentially it's giving you an indication of what your MAs, your moving average term should be. It'll become clearer once we do it. Here's the partial autocorrelation as well. Clearly something's going on. The first one's always correlated with itself 100%, but there's also something here going on with the second one as well. So how do we deal with that? Well, here's what we might do. We look at those pictures, we think maybe there's 2 terms, there's 2 AR terms that we have to take account of because those 2 periods were still significant, and there's something like 1 or 2 MA terms as well. So this 2 here is for the MA term. So again, the ARIMA takes into account the autoregressive part of the model, the differencing part of the model, and then the moving average part of the model. That's the only things you really have to worry about in an autoregression model. That's why they're so popular. Let's see if it runs now, if it's finished running now. So yes, indeed. So, and these outputs are the standard sorts of output. That's what makes it so nice. I think why people still generally like it a lot, because these terms are the standard sort of terms that you get from any sort of regression. And I think if you keep in mind that an autoregression is essentially a regressive type model, it makes things a lot easier, especially if you're adding exogenous variables, as I'll show you how to do later. So these P terms, I mean, the AR2 term is still a little bit, it's definitely not significant, 0.65, it's too high. Generally, the lower it is, the better it is. No one cares about the constant, so we don't look at the constant. But my eye always goes to the P term generally, and it's doing pretty well. The model's doing pretty well. Now it's easy to see how it changes. So we take an AR1 term, an MA term, and what we also look at here is the AIC. Because, I mean, it might be, I mean, you might say to yourself, well, why don't we just include as many variables as we want in there? What can be the harm of that? But you're getting overfitting. So this AIC term is called the Akaki information criteria, and it's essentially telling you, yes, you get a better model, but we're going to penalize you for adding an additional variable. It's like the BIC or the other information criteria. So, and the lower the AIC, the better the model is doing. So here we're at 14.61, and now we tried it with the 1.11 just to see what happened. It went slightly higher, so it's a slightly worse model. So we're doing pretty well. So our pictures told us pretty well what we needed to do. It still has some weightiness to it, and that's not surprising because we have the seasonality in there. We haven't really taken care of the seasonality. We saw that it changed a little bit, but not as much as to really affect it. And here's the essentially the plot of the estimated series, which is the red one against the blue one. So it's clearly doing something wrong still. It's not a happy model. But that's not surprising because we know we have seasonality in there. We have to take care of that seasonality somehow. So that's where this S ARIMA comes in. So this S ARIMA stands for seasonal. Now you'll notice that there's the AR term, the differencing term, and the MA term. But we also have the seasonal order, which is also, in this case, I just made up a number that would run quickly. We have a AR term for the seasonal ordering, that wavy part, and we have our original number of periods, 50. It's important to get that right. We have the differencing, and we have the MA term. So now we can run that. And this takes a little bit of time. takes about a minute, so we're getting close. There we go. Now we've seen, not surprisingly, the AICs dropped a bit because we've had also more variables in there, but the AICs seems to be saying the model is doing much better. Our p-values are kind of weird. We have some of them appear to be insignificant. Well, a lot of them are hugely insignificant. And that's just because I chose this model so it would run relatively quickly. If we had chosen one with the 2, 1, 2 for the normal ordering, and then the seasonal ordering of, I think it was 0, 1, 0, it does much better. Let's see what it looks like. It still has some, it's still not quite normal, so the residuals aren't normal. This seems to indicate that these are standard sort of outputs in diagnostics. There's still some curviness in there. That's because we chose a model that was parsimonious rather than exact. And it's taking care of a lot of that. A correlogram is the same thing as an autocorrelation function. So you're thinking, well, why are we doing all this? And here's the outcome. It does pretty well. So essentially the orange part is the real data, and the green is the estimate. It's still doing pretty well. So you might think to yourself, well, this clearly is, clearly you can use an automated system to do this because you're looking at, essentially what you're looking at is the AICs or the BICs, some way of measuring it. Just try out every permutation, find the best model. And that seems like a good idea, except it's awfully, awfully slow. So I generally recommend that you start out with a simple model. So this is the P term at 0, D is 1, Q is 1, or a 1, D of 1, and a Q of 1 with a simple REMA. And try out these ones first to see if the AIC moves significantly. If it does, then you probably want to, depending on which one caused it to move, then you want to move on to this auto-REMA. So this auto-REMA approach has quite a bit of variables or quite a bit of features that you can choose. The trouble is, like I said before, it's extremely, extremely slow. I've done this one with, you have seasonality true in this case, the starting P is starting Q, so where it starts when it's looking for the best model. Maximum P you can set to whatever, 5 or 6. Maximum D, you can actually over difference. So you generally want to have a difference of 1 or 2 in most of the data that I've come across. And then you do the same things for the seasonal part of the model. You check, this is augmented Dickey-Fuller test. Get your M in there, and this is critical because the default on the auto-REMA is actually an M of 12, which assumes that you have monthly data. So it's important to get that right as well. And there are other features as well. Stepwise goes you quickly through the system, whereas if you don't do stepwise, you do stepwise faults. It tries everything. So there are little sort of tricks to getting used to using this. But this one won't take long because I've put everything really low. And fires it out pretty quickly. And at the end, it's testing each of these. You can see what the AIC is doing. It's finding this one. And if you did it an exhaustive study, you would get a different model, of course. So what does the output look like? You get the S ARIMA. There's the model that you chose, and then you can run it again. And these are sort of standard outputs. This JV is looking at essentially how skewed the data is. And this the box one is looking at, are all of the features essentially significant? In this case, they are, except for the constants, which again, no one cares about. So ARIMA is really nice in the sense that it uses standard tools. It's quick to implement, relatively, once you have a basic idea of what you want to do. And because if you follow stationarity, then you know that the outcomes are legitimate in terms of you're getting the best possible estimators that you can get. So the best linear unbiased estimators. And it's quite easy to add an exogenous variable as well. So this is the same sort of model. I just created a same sort of data, but I added an exogenous term to it. So in this case, there's something happening between these two periods where it's changing the amplitude. And then you just essentially run it state space SMReMax with an exogenous variable. That's all you're doing, again, because it's just a regression. Change your orders, mess around with that if you want, and voila, you get your output. So again, and here's the breaks. We've made it significant, so happily it is significant in this case, and it's moving in the direction that we thought it would move. So it's quite easy to add these exogenous variables to ARIMA models as well. And it clicks pretty well, same sort of thing, the real data, and our data's over it, our estimate's over it. I mean, we're not really pushing the model, it's not really a fair comparison. So to conclude, this is just a singular sort of, this has only one time series in it, so it's the easiest of all possible cases. It allows you to do the inference if you've done your stationarity correctly. It's easy to extend, and it performs really, really well. So ARIMA and all the equipment there is available in Python or R as well. You just have to have some patience when you're running the models. And it's quite easy to extend it to other sorts of models. So for instance, if you're looking at 2 time series and you want to know the interaction between those time series, and you can run VAR models. And GARCH models essentially are looking at how things change, how permutations move through the time series. So these are all sort of extensions you can make to the model quite easily. So another approach is this profit model. And this is sort of the advertisement they do for it. So it does really, really well in some particular features. I mean, it's quite amazing how powerful it is out of the box, in the sense that it takes care of holidays. So if you put in Dutch holidays, it will take care of that itself. It looks for missing values and reports those to you. It looks for outliers and addresses those to you as well. It's just using a totally different sort of psychology, which is nice as well. It's doing these things where it's doing essentially a Fourier for the yearly. If there's yearly data in it, it's essentially a Fourier just essentially says, okay, we're not really interested in this relationships through time or anything like that. Just tell me what the curve looks like. We'll pluck that out in our component. And for weekly data and things like that, we'll just include a dummy in there. For trend, well, I mean, why bother with a linear trend? Why don't we just have a sort of a flexible trend? So if you're familiar with loose sort of LOESS sort of regression, it's a smoothing regression. The beauty of it is that it's not fixed, it's flexible, you can change these things. The danger of it, of course, is that you are also likely to overfit unless you're careful. The nice thing about the ARIMA is it's sort of automated that AIC or the BIC or whatever you choose to sort of panelize you is part of the system. It is part of the modeling process. This one you have to be careful about it. So let's go through an example. Yeah, it's in R and Python. It's an additive model, as I suggested. A seasonal component using Fourier, dummy variables for other sorts of variables, exogenous variables. It's nonlinear. It's flexible. And that flexibility, of course, comes at a cost. So what does it look like? Quite easy to do. And the nice thing is that it's using essentially data frames. So it's using Panda data frames. So in this case, in R, I guess it uses something similar. The only thing you really have to worry about, this is our original data. The only thing you have to worry about is renaming it. It doesn't like date, or data or anything like that. It needs to be DS and Y. Then essentially you create an object, you fit your data to it, you say how many periods in the future you want to go, and then it sort of takes care of all that for you. And there it is. Let's see what it looks like. Oops, in this case, it didn't do very well. And that's because you see, it's really not picking up, and certainly not as much as the ARIMA here. This is the real data, the black dots are the real data, and the estimate is these sort of wavy line that's going through here, and these are your kind of the confidence intervals. And I think it's a Bayesian sort of sit-up. So what happened? That's the first thing you think, well, something went wrong. The problem is, it's trying to do too much for you. So just like that M was important in the ARIMA models to get that right, this doesn't really even, it just says, well, you must be doing weekly, monthly, or yearly sort of data. But in fact, we're not. We have this sort of weird data where we have a periodicity of 50. In this case, it was 100 because I'm using an older data set. But in this case, it was a period of 100. We're not using data. So here's that same sort of M. So this is where you're doing all your sort of changes to the model. Oops. So here's that same profit, that M. So now we're adding in some more specific ingredients, so to say. So we have with growth, linear. We're saying we don't have daily seasonality, we don't have weekly seasonality, we don't have yearly seasonality. In fact, we have this other thing called experimental seasonality. You can make it whatever you want. And we know it's a period of 100. In this case, it used to be 50, and a Fourier order of 1. I mean, you can change that as well, too. So what happens? Now it's wonderful. You can see that.
What does the Fourier order of 1 exactly mean?
It's essentially thinking about how many curves you have in the data. Yeah, in your seasonality curve or in your yearly curve. Yeah.
One curve per period.
I'm not sure exactly what the translation is, but that's easy to fool around with. They make it really easy to do that.
Yeah, I guess so, because maybe 100 periods, the double frequency could also fit in it.
Yeah, we could try.
Maybe, yeah.
Yeah. And so now you see that it's fitting wonderfully. This right out of the box, you sort of expect it. That's not a surprise. I mean, it's that Fourier equation is picking out this trend wonderfully. Says no problem. I know what that is, and this would do really, really well. But so I'm not really using this profit to the extent that it can be used. Here's a more complex example, and this is the one that you always see in the examples. I don't know if you guys know who Peyton Manning is. Everyone's exposed to know who that is. No? American football. That's sort of the extent of my knowledge. He's an American football player. And this data is looking at the number of times his site got hits. So it's a pretty messy data set. And this is showing you essentially how to add holidays to it, or in this case, it's adding, because he's a football player, the important days for him will be things like playoffs. So Americans have during the football playoffs, you're playing against other teams in your league. And of course, the Super Bowls, he's been in quite a few Super Bowls. So these are special days for him. So you expect to see in your model, you can use your expert knowledge to fix these a little bit. And you simply add it in as a data frame.
So what does it actually do when you add those extra days in?
I think it's acting like a dummy variable. It's saying there's something else going on in these periods. Please take that into account.
And into account, what do you mean with that?
Well, in a linear regression, when you're doing something with a dummy variable, you're saying, tell me what the effect of that is after having taken into account of everything else to it. So that's it. So a typical dummy variable would be like for him, it's the Super Bowl. So the number of hits his sites are getting are different on the Super Bowl or after the Super Bowl.
Okay, yeah.
And this is saying, well, please include this additional piece of information in your model. So you're actually adding essentially another sort of feature to the
That would be an extra parameter, basically.
essentially an extra parameter.
Right.
Yeah. And this also runs quite fast. And you can see now the effects of the yearly sort of the effects. So apparently, I don't know, I think he was Super Bowl champion then or something like that. The number of times each year that things got hit, the weekly, so he tends to get more hits on Mondays. I guess that's explained because people saw the game on Sunday. Most of the games are on Sunday, so they take a look on Monday, what happened. And of course, during the sort of the trend over a particular year. And it happens to get better higher when they're in season, when they're playing football. So that's where I really want to leave it at this point. So profits, quick. There is flexibility to it. The downside is it's quite easy to add exogenous variables as well. The downside is probably overfitting occurs quite a bit. The ARIMA Classic performs extremely well. You need to be aware of particularly when you're talking more complex models, you need to be aware of the statistical assumptions behind it. But it gives you that sort of the ability to statistically infer, which is critical.
So I don't have much experience working with time series data, but how would you go about doing like cross validation or something like that to pick up this potential overfitting?
I think that probably the most obvious way to do that, I think, would be you simply say, okay, I have a 500 periods in my data. I'm going to essentially, in a simplified world, say take 400 of those, build a model, see how my model does, predicting the next 100 series, and compare. Because the beauty
You can't
of
just take random data points, right? Because they depend on.
you can't take random, so you have to
random
use.
periods.
That's really critical. To use that time element is critical too. And then essentially you can say, because the bottom line, what makes sort of time series so interesting is that, I mean, what you're trying to do is pretty easy. I mean, you just want to forecast. So I don't care what goes in the model, just forecast well. And that's one of the sort of the obvious sort of indicator of that is that you are forecasting well. I'm doing well. I'm not overfitting, or even if I am overfitting, I don't care as long as my results are good.
Yeah, you don't really need to validate as you need with neural networks, for example. Because if you've got your model, if the model is good, this already means that your parameters are not so bad.
Well, it depends. I mean, if you're using an ARIMA model, then if you're controlling for AIC or BIC, then it's taking care of that. It's already penalizing you. Now you might want to have a higher penalty at some point. But if you're doing profit, you're free to, make your trend as loopy as you want. As many Fourier curves as you want as well. Yeah. So do you have sort of the, please go ahead, yeah.
No, you have to finish.
No, I'm finished. Yeah.
So are there ways to take into account periods that are not fixed? So maybe periods that are growing, like now it's 10 and next is 11, 12 in a regular way, or that vary a bit, like next month.
Yeah, these are tough. I mean, these ones are tough. There's no real obvious way to do that. If it becomes a multiplicative sort of thing, so it's always getting higher, or the difference is always getting larger. Generally, what people do is they log it. So you log both sides, and then you.
But there's no way to use another algorithm to predict, or to find a formula that expresses the period.
You can always add in. You can always, because it's a linear regression, you can always make those changes if you like. You can. I mean, it's really getting into the details of how to do that are the interesting parts of the model. So if you have a changing period, obviously, maybe what you want to do is you want to weigh the ones that are at the end much more than the ones at the beginning. There's ways to do that as well. Yeah, but that's true. But if things are random, that's tough. Then no, I don't think any sort of system is going to be able to pick that up.
Yeah, no random, but
Increasing.
yeah, there is some regularity to it,
Mm.
but not obvious like in this example.
Yeah, these ones are clearly, cooked. Yeah. So are they sort of the differences straightforward? No. So did you want to introduce neural nets?
Yes, shall we have a very short break?
Yeah.
And then continue?
Great.
And then after it, you'll explain what the hands on.
Yeah.
Yep.
Do you need this? Or do you have some?
Well, I don't yet.